Welcome back, all of you, to part 2 of stereochemistry. Well, in this session, we'll be mostly covering the three-dimensional representation of the organic molecules and also their conversion into two-dimensional pictures. Well, this can be considered as the language of 3D chemistry or stereochemistry. And also it is very significant and handy in understanding the further sessions on conformation or optical isomers. Well, I have tried to put it as simple as possible, starting from the very basics and slowly building upon the concepts. I know some of you may not be having a natural inclination for organic chemistry, but need not worry. I hope this will be an enjoyable session for all of you. Let us move on. This is just an overview of the entire syllabus coming under this module, and in today's class we will be covering this part. So on to today's class on representation of 3D structures coming under stereoisomerism. Let us first have a look at the syllabus for today's session. The syllabus covers Newman projection, Sohor's projection, Wedge projection. All these three are three-dimensional representations, and also Fischer projection, which is a 2D representation, and their interconversion also. And we are going to try these on substituted methane as well as substituted ethane. Well, those who were not very keen on learning organic chemistry in your school classes need not worry at this point of time, because I'm planning to start right from the basics. So in the coming slides, we will be slowly building upon the concepts. So please be attentive. Starting from the very famous story of carbon, it has sp3 hybridization and the structure is tetrahedral. The bond angle is 109.5 degrees when all the bonds are sigma bonds or single bonds. A 3D representation of a methane, the simplest organic compound, is shown over here. Methane is very familiar to us. CH4, a carbon surrounded by 4 hydrogen atoms. Please have a look here. This is a tetrahedral structure where we have placed the carbon at the center and it is surrounded by 4 hydrogen atoms shown as white balls around it, connected to the central carbon. And you can see all the 4 CH bonds are oriented in space in different angles, in different orientations, and the bond angle will be exactly 109.5 degree. But how can we represent this on a piece of paper? That representation of a tetrahedral retaining its three-dimensional nature is shown over here. We will see about it in detail in the coming slide. The 3D representation of a methane. The tetrahedral structure with the bond angle 109.5 degrees. When we represent this on a plain paper retaining the three-dimensional structure, we get something like this. This type of representation is called a Wedge model. It's a 3D representation. Well, here, the bonds on the plane of the slide are drawn as straight lines. What do you mean by that? In a three-dimensional tetrahedral structure, the bonds on the plane of the screen on the slide, if you take the plane of the slide, you can see this hydrogen and this hydrogen are on the plane of the slide, right? These two are shown by straight lines. Here you can see. Please have a look. This and this. So these two represent these two bonds which are on the plane of the slide. Now, the bond projecting towards the viewer, which is this one, is shown as a thick wedge. This one projecting towards you is shown as a thick wedge. That is what you see here. See, the one which is projecting towards us is shown as a thick wedge. Now the last one, the bond projecting backward, which is this one. The projecting backward, the one which is projecting backward, is shown as a dotted wedge. Here you are. The one which is projecting backward is shown as a dotted wedge. So this is how you convert a three-dimensional tetrahedral structure onto a paper in a three-dimensional wedge dash model. I hope it is clear to you all of you. Here we have something very interesting and at the same time very significant too. We are going to convert a three-dimensional representation of methane, which is known as wedge dash model, to a two-dimensional representation, which is known as Fischer projection. How do we do that? We already know that in this, the straight CH bonds, please have a look. The two straight CH bonds here are going to be represented by a vertical line in Fischer projection. Fischer projection has vertical lines as well as horizontal lines. So these two lines, these two CH bonds represented by straight lines go to a vertical line. Now, two more hydrogens are left or two more CH bonds are left. One towards us and the other away from us. Well, when we take a look at this molecule from this side, when we are looking from here, the hydrogen shown in red color is towards our left hand side and the hydrogen shown in purple color is towards our right hand side. Well, when we convert this into a Fischer projection, these two go to a horizontal line retaining their position. Left hydrogen goes to the left hand side and right hydrogen goes to the right hand side. So this is a very simple and a very useful representation, Fischer projection. Later on we're going to see that this will come very handy especially when we assign notation like RS notation, etc. Please also note that the point where these two lines cross, the vertical and the horizontal lines cross, we have a carbon atom. This carbon atom is at this junction. And usually this carbon atom is not shown, but it is understood that there is the carbon atom. Now let us have a look at the Wedge-Fischer conversion of a substituted methane. We have already seen methane. Now we'll see how it works on a substituted methane. Well, here we have the substituted methane and it is just the same story as we have seen in the case of methane. That is, the straight lines are represented by a vertical line and the one which is away from us and the one which is towards us. When we view the molecule from this side, Q towards the left and QR towards our right. Similarly, we are representing it here also. Q on the left hand side and R on the right hand side. The thing is, all the hydrogens are replaced by different groups. So this is the conversion from Wedge to Fischer in the case of a substituted methane. This picture is very simple when we already know the conversion of methane. The next in the syllabus is substituted ethane. Before that, let us have a look at ethane because that is more familiar to you. Ethane, as we all know, has two carbon atoms. It is CH3 molecular formula, C2H6, and the structural formula is something like this. The two carbon atoms connected to each other and each carbon has 3 CH bonds around it. Well, in fact, if you consider the three-dimensional structure of ethane, the ethane can exist in two different forms. One is called the staggered and the other is called the eclipsed. This is possible because of the free rotation of the carbon-carbon bond. We will be seeing this in very detail in conformations, but for the time being, please understand that because of the rotation of the CC bond, the CH bonds will be oriented in space as distantly as possible so that the total energy of the molecule is minimum and the stability is maximum. Such an arrangement is called a staggered arrangement. And think of the opposite. An arrangement which gives it maximum energy and which gives it minimum stability. That is called eclipsed. We would never be able to understand it looking at a two-dimensional picture. We need to have a 3D representation to understand it further. That is the reason why we have these three-dimensional representations. What are they? One, of course, is called the Newman projection model 3D representation. The second one is Sohor's three-dimensional representation. Now the last one, third one, which is familiar to us, that is the Wedge dash three-dimensional projection. These three-dimensional pictures will help us in visualizing the chemistry of ethane much better. Substituted ethane, and now I guess we are ready for this because we already know the story of ethane, and the story of substituted ethane is somewhat similar to that of simple ethane. Here also two representations, two arrangements are possible. One is called eclipsed and other is called staggered. Staggered with maximum stability and minimum energy, eclipsed with maximum energy and minimum stability. Well, both these arrangements can be represented through 3D representations using any of these three methods. One is called the Sohor's method, the next one Newman method, or the Wedge dash method. Starting with the first 3D representation, that is Sohor's projection. We are going to consider the example of substituted ethane. Well, before we move on to the example, the Sohor's projection usually represents the carbon and its substituent groups as either the capital letter Y or an inverted Y. Let us have a look. The staggered substituted ethane, an inverted Y. At the junction of these three lines, you can have the carbon. The carbon is attached to three different substituents in an inverted Y manner. Okay, now the first carbon is connected to the second carbon here, and the second carbon can be represented as either an inverted Y or a straight Y. Let us see. Here we are representing it as a straight Y. The carbon at the junction is connected to three different substituents X, Y and Z. You must have noticed the first one is an inverted Y and the second one is a straight Y, which means all the bonds in a three-dimensional representation are oriented as distantly as possible, giving minimum energy to the molecule and maximum stability also. So this is a preferred form and it is called the staggered representation. Now let us see how an eclipsed representation looks. Before that, we are going to try to convert this staggered model into the eclipsed model. How can we do that? All this is possible because of the free rotation of the CC sigma bond. We are going to fix the first carbon here. We prefer to do that here. It can be done in different ways. Here in this case, we are going to fix the first carbon and we are going to rotate the second carbon. Let us consider a rotation of say 180 degree. If we fix this first carbon and rotate this through 180 degree, what happens? X goes to the diagonally opposite place here and Z goes to the diagonally opposite spot here and Y goes to the diagonally opposite spot here. This leads to something like this. The first carbon is fixed, no change at all. PQR, no change at all. Connected to the second carbon and the second carbon is undergoing a rotation through 180 so that now it looks like an inverted Y and X goes here, Z goes here and Y goes here. All are exchanging positions and here you can see both these bonds are parallel to each other. The angle between these two adjacent bonds projecting upwards, this is called the dihedral angle and the dihedral angle is minimum here, whereas here it is maximum. So here, this kind of representation is called the eclipsed representation, with maximum energy for the molecule and least stability. So that is the representation called the Subhash projection. Now coming to Newman projection. Newman projection is very similar to Subhash projection. The difference is that the CC bond is represented by a circle here. Please have a look. Again, we are representing it as a Y, inverted Y. Then the CC bond is represented by a circle, and we have the Y, that is a second carbon atom, just like that, whatever we have seen in the previous case. So obviously, we are going to fix this front carbon and rotate the back carbon to 180 degree so that we get the eclipsed model. You have to draw along with me the fixed first carbon. Then we have the CC bond as a circle, and then finally we have the 180 degree rotated second carbon. The substituent X goes up, Y and Z change positions. Well, this is the eclipse one. As we have seen in the case of Subhash model, staggered is having maximum stability and eclipsed is having maximum energy or least. So now we have an idea of 3D representations and various arrangements. Now we are ready for conversions, interconversions, or how a 3D representation can be converted to a two-dimensional Fischer projection. Why should we do that? Because Fischer projection is a more friendly, more useful, more understandable representation. This comes very handy when you study about RS notations and all. So let us try to learn more about that. In 3D 2D conversion, the first thing that we have to keep in mind is staggered structure, which is a 3D structure, to Fischer, which is a 2D structure, is not possible. If you have a staggered structure, you have to first change that to eclipsed before you do the conversion to a 2D. Staggered to eclipsed to Fischer. This has to be kept in mind. Considering the conversion of a real example, here we have a Newman projection of a substituted ethane. And on the first look, we understand that this is a staggered one. So first step, before we convert this into a Fischer, we need to convert this into an eclipsed form. How do we do that? We already know how to do that. We retain the first carbon or fix the first carbon as such, and then we rotate the second carbon so that now the second carbon is an inverted Y with X on the top, Z and Y changing the positions, exchanging the positions. So this is the eclipsed form. Now the eclipsed form is ready. Now we can convert this into a Fischer projection. Now Fischer projection, we have some idea about Fischer projection because we have already seen this in the case of methane. Fischer projection, as we know, has vertical lines and horizontal lines. The vertical line and the horizontal line each showing a carbon on the main chain. If there's only one carbon on the main chain, then we can show only one line. But here in the case of an ethane, substituted ethane, we have two carbon on the main chain. So we are going to show it as two horizontal lines. Well, now the question is the front carbon. Where to place the front carbon on the Fischer projection? Well, we know that the front carbon is fixed in this case with P on top and Q on the left and R on the right hand side. To retain that orientation, carbon 1 or the front carbon has to be placed over here. See, now you will understand this one. The carbon 1 retaining the position of P, Q and R. It is a fixed one. Obviously, the second carbon will be here. The second carbon has Z to the left and Y to the right. Let us retain the positions. Z to the left and Y to the right. Now X is only one position to go, and that is here. So this is how you represent a three-dimensional structure on a planar model, that is a two-dimensional Fischer structure. So Newman is over. On to the conversion of a Subhash staggered to a Fischer. It's a staggered one. Substituted ethane. First of all, we are going to convert this into an eclipsed form by fixing the front carbon and rotating the back carbon. We prefer to do it by rotating it through 180 degrees. That's all. Yes. So this is the structure that we get. Now, in a similar manner, as we have seen in the case of Newman, we are going to convert this into Fischer. Fischer has vertical lines and horizontal lines. Here the vertical line is drawn and 2 carbon atoms to be shown. So 2 horizontal lines are here. Now, just as we have done in the case of Newman, the first carbon is fixed. So the orientations have to be kept. The first carbon has to be here. Yes. P, Q, R, retaining their orientations. And the second carbon Z and Y go here. And X comes to. It's nothing but a replica of the conversion of Newman. Let us consider one more example before we wind up. Here in this example, the orientation is slightly different from the examples that we have previously seen. The first carbon itself is a Y, is a straight Y. And the second carbon is also a straight Y. So is this an eclipsed orientation or a staggered one? Definitely it is an eclipsed one. So there's no further need for converting to eclipsed. It's already in the eclipsed. Straight away we can go to the conversion to the Fischer model. Okay. Here we are to the Fischer model. Now Fischer, as we know, has vertical lines and horizontal lines. How many carbon atoms are here in ethane? 2. So we have 2 horizontal lines. These all we have seen in the earlier cases also. Now, where do we place the front carbon? Retaining the orientations of the front carbon with P downwards, Q on left and R on right. As such, this is going to be placed over here. So that now P is going to look downward, Q on the left and R on the right. See? So we have the first carbon placed here. And obviously the second will be here with Y on the left and Z on the right. X has only one place to go and that is here. So the conversion is done. That's it guys for now. Practice as much exercises as possible so that you will be thorough with the concept. Thank you so much for listening to me. Until we meet again for the next session, it is bye from me. Till then, stay safe, stay happy and take care. Bye-bye.